So here's the fundamental theorem of algebra. We've talked before that an nth degree polynomial can have at most n real zeros, or up to the n zeros, meaning that a fifth degree polynomial, for example, can have up to 5 zeros, up to 5 roots, up to 5 solutions there, or x-intercepts. If we add in the complex number system, we can improve on that. Specifically, we can say it has exactly n zeros. So if a fifth degree polynomial, if we include the complex number system, has 5 zeros. This is derived from the fundamental theorem of algebra, which says that a polynomial of degree n, where n is a positive integer, has at least 1 zero, meaning n can be 1, so it would have to have 1. This also leads to the linear factorization theorem, which everyone's familiar with, meaning that, for example, if you have a solution x equals 3 is a root or 0, then x minus 3 is a factor. And combining that with the fundamental theorem, we know that x minus c, being a complex number, is a solution. And one more thing about the fundamental theorem of algebra is that it's an example of an existence theorem, meaning it just tells you that these solutions or these zeros exist, but really doesn't do any good in helping you find them. It doesn't tell you how to find them at all. Nevertheless, it is an important theorem in algebra. So if we're going to have complex solutions or complex zeros, it's important to know what they look like. So if we have any complex number, the form that is always in is a plus bi, where bi is the imaginary part of that complex number. And if I have a solution, a complex solution to a polynomial, they always occur in conjugate pairs. So the complex solutions to a polynomial equations always occur in conjugate pairs, meaning if 2 plus 3i is a solution to a polynomial, 2 minus 3i must also be. So a quick review of something we already know is that if I'm given zeros of a polynomial are 7, 3, and negative 6, I can ask, well, what do you know about the factors? Well, we know the factors must look like x minus 7, x minus 3, and x minus negative 6, or x plus 6. So I just plop an f of x in front of that, and I have a possible equation. Now, the only thing is, and to generalize it, we can put a coefficient in front, and that would say, okay, if I put some a there, that's going to cover the whole family of functions that have that. But in general, what's in red is what's a possible solution. So I'm going to extend that previous question to say, write a polynomial function with real coefficients that has the following zeros. So you have the 0, 5, which that's going to give us the factor of x minus 5. 2 is going to give us a factor of x minus 2. 3i is going to give us a factor of x minus 3i. But as we said before, I have a complex solution. The conjugate is also a solution. So I know there's another 0 that they're not telling me that must be negative 3i, the conjugate of positive 3i, and that would give me a factor of x plus 3i. Now, I'm not finished with this. I want to multiply that out because it says that I must have real coefficients. Well, I have i's in here. So how I'm going to do is I'm going to multiply them out. And I actually think it's easiest to multiply those terms first, because when I do that, when I get x squared plus 3ix minus 3ix, those i's are going to cancel. And then my final term would be negative 9i squared, which is actually going to be a real number. That's the big deal with the conjugates. So that part is x squared plus 9. And when I FOIL or multiply out these, I'm going to get a trinomial of x squared minus 2x minus 5x minus 7x and plus 10. And all that's left is to multiply those out again, which is going to give me x to the 4th plus 9x squared minus 7x to the 3rd minus 63x plus 10x squared plus 90. And then combining like terms and plop, again, throwing a nice little f of x in there to make it look a little fancier and show that it is a function. And x to the fourth minus 7x cubed plus 19x squared minus 63x plus 90. And there, that would be a polynomial function with real coefficients that has those zeros. So now we're quickly going to look at a problem that's going the opposite way of what we just did. And this one, the first one is going to be something you'll be much more familiar with. And the process in general is something you do a lot more. And with this one, I'm just going to try factoring. So I'm going to say, let's see, this can factor into x minus 8 times x plus 2, which would give me solutions, or zeros, of x equals 8 and x equals negative 2. So there's nothing crazy about that. But what if I kind of switch this, I change this equation? And what if I originally gave f of x equals x to the fourth minus 6x squared minus 16? And no, first thing people might get a little stumped on that, but it follows exactly the same pattern. And so what that means is my factors would be x squared minus 8 times x squared plus 2. And now if I'm including irrational numbers as well as imaginary numbers, I can factor this further. The factor x squared minus 8 is irreducible over the rational numbers, and x squared plus 2 is irreducible or non-factorable over the real numbers. But now everything's fair game, so I can actually factor this further. So x squared minus 8 can factor into x plus the square root of 8 times x minus the square root of 8, and we can worry about simplifying that further later. And x squared plus 2 can factor into x plus I square root of 2 times x minus I square root of 2. And then, so if I was going to name all my solutions in this case, I can write x. So this is now a product of linear factors. I have x to the first in every single term. And my solutions, or roots, or zeros of this polynomial would be x equals, I guess I don't need to write it twice, x equals plus or minus the square root of 8, which we can write as 2 square root of 2, and plus or minus I square root of 2. Again, according to the fundamental theorem of algebra, I have 4 solutions. So following the previous example, we could try to factor x squared plus 48, since it's not a sum of perfect squares, but it is a sum, and then we can use the square roots. But this might help illustrate another way to find what those two factors can be. And I'm going to do this by first moving the 48 over to the other side and taking the square root of both sides. Now, since I am introducing the square root, I must use plus or minus the square root of negative 48. Since I have the square root of a negative, I'm going to, and I'm sorry, that is not x squared anymore, and I'm going to take out an I, and then the square root of 48 can break down to, well, let's say that's the square root of 16 to the square root of 3. So x equals plus or minus 4i squared root of 3, and those are my solutions. So here's one last example, and there's nothing special about this. So I encourage you to pause this now and then come back and check your answer if necessary. So this one will factor, I'll set it up, I forgot to change colors, into x squared, I have minus 16 and plus 4. Simple difference of squares, x plus 4, x minus 4, and I have a sum of squares which is factorable over as long as I include complex numbers, and that gives me x plus 2i, x minus 2i. So my roots, or zeros, or x-intercepts of this function are plus or minus 4, plus or minus 2. And again, consistent with the fundamental theorem of algebra, I have degree of 4. I have 1, 2, 3, 4 solutions over the complex number system.